Hello everyone, welcome to problem 3.24 of David Griffiths Electrodynamics. So, today's problem says to solve Laplace's equation by separation of variables in cylindrical coordinates, assuming there's no dependence on z, in other words, cylindrical symmetry, make sure you find all solutions to the radial equation. In particular, your result must accommodate the case of an infinite line charge, for which, of course, we already know the answer. All right, so we're kind of just going to jump right into this. There's a lot to cover here. So, Laplace's equation simply states that the Laplacian of the potential is equal to 0. And, I thought about going through and deriving the Laplacian in cylindrical coordinates, but I just decided not to. David Griffiths, the textbook, if you go to the covers, either the front or the back cover, gives you what the Laplacian is in different coordinate systems like spherical and cylindrical. So I basically just took it out of the book. If you're actually curious of how to calculate the Laplacian, there's plenty of resources online. Just Google deriving the Laplacian cylindrical coordinates, you'll find something online that kind of help you. But eventually, if you use just the textbook, you get this equation here. And so this is the Laplacian expressed in cylindrical coordinates, where we're using the coordinates s, phi, and z. So, if you have some cylinder, right? What we're saying is the coordinate system is s is the distance this outward from the z-axis, phi goes around the z-axis, and z is the vertical height. And this is the Laplacian. The problem states that there's no dependence on z, so any derivatives here which had to do with z are gone because the potential is not dependent on z. Therefore, any derivative of that potential would be 0 with respect to z. So this is the Laplacian only with terms involving s and phi. And then, of course, this is equal to 0. All right, so using separation of variables, we look for solutions. We look for potentials as a product of two different functions that are independent of each other. We have a capital S, which is a function of little s, and then a big phi, which is capital little phi. I admit the lettering here I chose is a little confusing because the actual function is, the function letter is the same as the independent variable letter. So I try to be explicit where I can, but I'll try to just point out which one's which where I can. So if we take a solution of this form and plug it in, we have 1 over s. So this is the independent variable s, like little s here. Partial derivative with respect to s of s times s prime of s. I'm really wishing that I chose a different name here, but oh well, we're going to get through this. So any derivatives, like s prime, is like the derivative of the function. Any s's outside like this are probably the the actual independent variable. So with s times s prime times phi of phi plus 1 over s squared phi double prime times s equal to 0. So that's just plugging in this for v into the equation. We divide then by our product of these two functions, and what we get is the same thing, except we now have these two terms here. Well, after you multiply by s squared. So if you multiply s squared, what you get is s times partial derivative with respect to s times s times s prime divided by s. So this is the derivative of the function s divided by the function s, and then plus phi double prime divided by phi equal to 0. And I hope this is making it clear that these are, when I have the parentheses around it, that is the function, not the independent variable. So we have these two terms here. One term is all in terms of s, one is all in terms of phi, and they equal 0. So if this one changes, then this doesn't change because this is independent of phi. So as phi changes, this doesn't change. But if phi changes, then this, for it to still be 0, this must change. So what that means is that these two values must be a constant, two different constants, so that they both add up to 0. No matter if you change this, then this value must change accordingly. So we can set each of those terms equal to some constant C1 and C2, where we know that C1 plus C2 is 0. Basically just rewriting this. And taking the phi equation and rearranging it, so multiplying by phi and then subtracting over, we get phi double prime minus C2 times phi equal to 0. And we know that, if you just take and solve this differential equation, this is a second order constant coefficient differential equation. It's homogeneous. There's the solutions to this are pretty known. Depending on what, if C2 is negative or positive or whatever, you get different solutions. If C2 is negative, then this becomes a plus, and you get sinusoidal solutions, which are periodic. If you keep C2 positive, and so this negative stays, then you get exponential solutions. So geometrically, the dependence on phi should be periodic, because as you go around some distance phi, eventually you'll come back to the same point. So at every 2 pi, every multiple of 2 pi, you'll come back to the same point. So the potential needs to be the same at that point, regardless of how many times you've gone around. So this geometric constraint on the problem means that we know it can't be exponential solutions because exponentials aren't periodic. So we know that the sinusoidal solutions must be, make physical sense. So we know then we put the constraint that C2 must be negative, so that we get the sinusoidal solutions out of this equation, and we conveniently set C2 to be negative k squared, where k is just a constant, just sort of a rewriting of this constant, and the k squared is just makes it nicer in the end. So our new equation to solve is this equation, which of course we know the solution to. This is a very common differential equation in physics. Phi double prime plus k squared phi equals 0. The solution to this is a, which is a constant, some arbitrary constant, times cosine k phi, plus b, which is another constant, times sine k phi. And so this is our known solution for the phi equation. And given that we know that the part of the potential, depending on phi, must be the same at phi plus 2 pi, meaning the potential at some value phi must be the same at that value phi plus another 2 pi, because that's the same point mathematically. This puts a constraint on k to be an integer, so that it always is integer, so that the k here inside the argument of cosine and sine must be an integer, so that you're only going, it's only going to go by multiples of 2 pi and not like some decimal value of 2 pi. Because if k could be a decimal, then when you phi plus 2 pi would be not be an integer multiple 2 pi anymore, and you get a deviation from that, and you're no longer at the same point. So, and we know it has to be periodic, so that puts a constraint for k to be an integer, and it could be 0. There's nothing saying it can't be 0, but it could also be 1, 2, 3, whatever. So that's the constraint there. And then moving on to the radial equation, we have this form. And what we can do is actually rewrite this. So let me rewrite this. If we actually do the derivative here using the product rule, we get s and then times s prime plus s times s double prime. Because, and this is just doing a product rule in these two terms here, and this is still equal to k squared times s. And then distribute the s through, you get s squared s double prime plus s times s prime minus k squared. So moving that over, so minus k squared s equal to 0. So you might actually recognize this. This is a Cauchy-Euler differential equation, because the power of the independent variable here on each term matches the derivative, like the derivative number. So this is a pretty common type of differential equation that you learn to solve in, a standard differential equations class. And so the way to solve a Cauchy-Euler differential equation is to assume that the function is of this form. So our function capital S is equal to the independent variable s to the m power. If you take the first derivative, we get m times s to the m minus 1. Then take another derivative, we get m times m minus 1 times s to the m minus 2. And so that's just getting each term, because we're going to have to plug it in. So plugging everything back into the equation, what we get is s squared times m minus 1 times s to the m minus 2 plus s times m times s to the m minus 1 minus k squared s to the m equals 0. And so we have on this first term, s to the m minus 2 times s squared is just s to the m, and then s times s to the m minus 1 power, those multiplied together just also give us s to the m. And then on the third term, we still have s to the m, so we can factor out s to the m. So, I just rewrote it here with everything in terms of s to the m. And then I factor out s to the m here and set it equal to 0. And if you recall, I just wrote a short thing here. It's not really important, but the Cauchy-Euler form is ax squared y double prime plus bx y prime plus c y equals 0, where in our case, a is 1, b is 1, and c is negative k squared. It doesn't really matter here, but I wrote it down anyways. So we know that this term here, we have a product now. This s to the m power can't be 0. There's no way for it to be 0. Even if m was 0, you get 1. So there's no way for this term to be 0. So that means this term must be 0. So this is our characteristic equation. So we set that equal to 0 and solve for m. And so just multiplying through, we get m squared minus m plus n minus k squared equal to 0, which gives us m squared minus k squared equal to 0, which then gives us the constraint on m, that m is equal to plus and minus k, by just taking the square root there. And we also know from our previous work on the phi equation that k must be an integer and real. So we have these roots are distinct real roots, which for a Cauchy-Euler equation, the solution that we said was s is s to the m. So our solution is just for the two values of m, we just have a superposition of these two possible solutions. So our solution is s is equal to c, which is some constant, times s to the k for the first m value, and then plus d, which is some arbitrary constant, times s to the minus k for the second value that n could be. So just adding the two different solutions together gives us another solution. And then this is, so with this form, we have to consider what happens when k is 0. So if k is something other than 0, we just get this form of the equation. But if k is 0, then what do we get? So if you plug in 0, then this becomes 1, this becomes 1, and you get two constants that add together, and so you just get a constant. So when k is 0, we get a constant. We don't know what that constant is, but we know it's going to be a constant. And so we got to treat the k equals 0 case separately. So let's kind of look at, this is what we get when k is not 0, but let's see what the solution might look like when k is 0. Actually, I've got to flip it around the other way. 1 second. All right, so if k is 0, then, let's just looking at the original equation for the differential equation we started with, right, for s. Remember, this s is the function, so we know what this equation is saying is that the derivative, if you remember, there was a k squared over here. Let me just kind of recall. So the equation we're using is this one right here, right? This is what we started with. But if k is 0, then this whole side is 0. So given this, what this is saying is that the derivative of this term, s times ds by ds, is 0. So that means that this must be a constant, right? So s times ds by ds is a constant because the derivative of a constant is 0. And so just dividing by s, let's just call that constant c, and then just integrating both sides with respect to s. What we get is, this is just the fundamental theorem of calculus here, so taking the integral of this derivative just gives you the function s. So the function s of s is equal to, and the integral of 1 over s, remember c is a constant, so 1 over s is the natural log of s times c, plus another arbitrary constant because this is an indefinite integral, so we add another constant. Let's just call it d. So this is the form of s if k is 0. And this is a constant, so choose any value s. It's a constant times the natural log of s. Well, the natural log of some number is a constant, plus another constant, you get a constant. So we know that we knew that the solution is constant, we just didn't know the form of the constant, and this is the form of the constant, given that k is 0. Now, let's quickly look at the phi equation, because the phi equation also, has k in it. It is right here, so what if k is 0 for that equation? Let's look at that case. So we start with this equation where k is 0, so the right-hand side is 0. So it's d squared of phi by d phi squared. This is the second derivative. And I'm running out of ink here, so let's swap to another marker, perhaps? Yeah, that works. So if the second derivative of phi is 0, that means the first derivative of phi must be a constant, correct? So because the derivative of some function of a constant is 0, so taking this and integrating both sides, what you get is that phi, as a function of little phi, is equal to b, because integrating a constant, you pull it out, right? So it's just b plus a times phi. And so looking at this, we know that the phi part of the potential needs to be periodic. So the fact, a constant would be periodic, something staying the same no matter what is quote unquote periodic, it doesn't change. But because we have a phi, plugging in a times phi and then adding another 2 pi isn't going to be periodic. That's not going to be the same number. So due to this, we know that this physically doesn't make any sense. So therefore, we know that this part of the solution doesn't exist, at least for k equals to 0. That doesn't mean that for k equals 0, that doesn't mean that this doesn't exist. This doesn't break any rules that we found so far, but this does. So for k equal to 0, eventually we're going to sum up over all our solutions for all k values. And for the k equals 0 term, this won't be a part of the solution. So this is just something we've got to keep in mind. And so if we just write, for some value of k, because all of our stuff has been dependent on this value of k so far. So if we just pick some number k, we could write our solution, or a single solution, because we have multiple solutions for different values of k. We could write a single solution of form, v sub k of s and phi is, our product of these two functions. And so we know s is of this form, c sub k times, which is a constant that depends on what k is, times s to the k plus d sub k, which is another constant, times s to the minus k, right? That was what we found before for s. And we multiplied by phi, which we found was, a sub k times cosine k phi plus b sub k times sine k phi. Just multiplying the two solutions we found. However, this is just a single solution, so to get a more general solution, we sum up over all values of k, but remember, we have a special case to treat for k equal to 0. So I actually pull out the k equals 0 terms and start with the summation at k equals to 1. But we know at k equal to 0, there's no phi term because it doesn't physically make any sense. So all we're going to get is one term here for k equals 0. So we have some constant a naught, which is what d would be, plus b naught, some other constant, and I call it b naught a naught because it's the 0th term here in the summation, times the natural log of s. So we have this initial starting two terms for k equal to 0, then plus the summation of k equals 1 to infinity, and now we have our full solution. So what I do here is I distribute this across both terms here, and that's really it. So, and then I just pull out the s sub k and s minus k here. So just to kind of make it clear, so we sum up over all k's from 1 to infinity, and then we have s to the kth power. Distribute this through, so we have then times c sub k times this term, a sub k cosine blah blah blah, plus s to the minus k, so I put that out front, times d sub k times all this, so distribute that through. So that's one way to write it, and again, I just rewrite it here, so we have the terms out front here. All I did here was combine the constants of c sub k and a sub k and d sub k and a sub k and b sub k are all constants, so we can combine them into just single constants. So I just write this as s to the k times a sub k, which is some constant, which is the combination of these two, times cosine k phi plus b sub k, which is the product of these two, times sine k phi plus s to the minus k, and then I have c sub k, which is the product of these two, times cosine k phi plus d sub k, which is the product of those two, times sine k phi. And this is the final form of the solution. So this is what Laplace's equation gives you for cylindrical coordinate system with azimuthal, or sorry, cylindrical symmetry with no dependence on the z parameter. So I know that was a lot, so if you guys do have any questions or need some clarifications on some things, or if it was hard to read, I hope I at least explained it well. So yeah, thank you guys for watching. Thanks for all the support you guys give and all the great comments. It's really appreciated. I finally got my channel monetized, so that's a big step for my channel. So I'm really excited for what the future holds for this channel, and hope to bring more content like this to you guys for years to come. So thank you guys for watching, and have a great day.